So this is Women Who Code Python. Thank you everyone for joining in tonight. I appreciate you. Sorry we started a little late. I just had a little issue with the webinar. We were on time, but I just forgot to click one button and I missed it. So, but we're here. Let's get started and don't lose more time. So as we always do, we're gonna talk a little bit about where we are in Women Who Code and our mission, which is the most important part, which it is dedicated to inspire women to excel in technology careers. The Women Who Code goals are empower with the skill needed for professional achievement, educate better, build a community, develop role models. And we have also important, we have coding resources, we have leadership, we have global community, we have a community job board, which you can go online and get some information from. And as well as you have the applaud her that you can send it all the time if you want someone to be recognized for some kind of work they have done and any professional achievement, you can do that as well. And we also have the code of conduct. We are in Women Who Code is an inclusive community. This is available for everyone who wants to join us. We are really open. There is no physical orientation, nor appearance, nor body size, anything. So as long as you are okay with our mission and you support that mission, you are welcome. All right, I talked about this. And we have different tracks. We have front end, we have blockchain, we have Python, which is us. We have mobile, we have cloud, and we have data science as well. I also want to thank the sponsors that without them, we couldn't be able to do this, which is McKinsey, Python Foundation, and Home Depot. So now, the last thing, if you are not a member, please join us. You can go to womenwhocode.com/Python and you can be a member. It's free. And if you join, you will see all the upcoming events. You will get a newsletter with job boards, and they even have some scholarships, some really good information they send weekly. So besides that, so we have tonight a webinar, which is about the Emoji Predictor. We have here Alex, which I'm very happy and excited to have her here tonight to talk about it. And her name is Alexandra, but she said, let's not. So I don't know about that, but she's in El Paso, Texas. She graduated in computer engineering in a cyber community minor at the Texas A&M. She works for Lockheed Martin Aeronautics, and her interests are DevOps, data science, Python, Agile. It looks like she has really, really a strange love for the workflow, so interesting. She likes soccer, dancing salsa, and actual salsa. And she started always with sentences that say, so I was listening to this podcast. Very important to know about her. And she really have interesting goals. She wants to get a psychology degree and be a professional counselor. Interesting. And she's part of organizations like Big Brothers, Big Sisters, and Girls, Inc. She loves to help people and realize what they can do once you remove the theme veil that externally impose and the self-imposed social construct, ideas, and fears. So, you can do it. Everyone can do it. So I'm going to stop talking and I'm going to pass this through her.
Awesome. All right, how do I present my screen?
Let's see. So you should be able to have an option to share the screen, I believe. Do you have an option?
Share.
Okay, let me stop sharing.
There it is.
Stop sharing.
Here is it? There.
There it
Is
is.
it visible?
Yes.
Yes. Okay. All right. I guess I'll get started. All right. So I hope everybody's doing well this evening. I've ran through this tutorial a couple of times. Each time it was different. The hardest part is always starting. So let's see. So I chose emoji prediction, or more likely
Oh, wait,
machine
one
learning.
second. One second. I think they're saying they can hear you very well.
Oh.
Let me mute myself just in case. Just
Hello?
a second. Let's see. Chat participants. I'm gonna mute myself. Okay, I'm gonna go ahead and mute. Just go ahead and talk again, and let's check that first.
Okay, hello, is this good, bad? Good stuff? No? Yes? Good? Okay. How about now? I have a pretty bad mic. It's just my headphones. Not anything professional. Okay, cool. So at the end of my, not as good, can't hear anymore. Oh no. Okay. I guess, okay, I'm just gonna hold it next to my mouth for the rest of this. Okay, yeah. Okay, cool. All right, yeah, I just need to hold it right next to my mouth.
Yeah, you need that, and that sounds perfect.
Okay, it's literally an inch from my lips. Cool.
You got this.
Okay. All right, so I'm gonna start over. So at the end of my senior year of school, I joined this class. It was a natural language processing class, and it was super interesting. But one thing that I did have trouble with is figuring out how to start. And this is a machine learning problem, and it's kind of hard to get started because you don't really know what's going on. And so what helped me was that one of my friends, he had done a similar project, and he just walked me through it. And turns out it's actually pretty simple. And as you'll see, this is a very simple. The project itself is about like 10 lines long, which is pretty cool, but you still need to know a couple of concepts. So let's start. So I chose emoji prediction because I think it's pretty cool, the things you can do with Twitter and data mining and data science. So let's start with natural language processing. So what is natural language processing? Well, I'll show you some applications of natural language processing so you can kind of get the gist of what it is. So let's just show you a couple of applications. And it's basically just how computers interact with human language. So this is kind of what we're going to be doing, text classification. And it's one of the problems of machine learning, just classification in itself. Something you can do with that is spam filtering, language identification, blah, 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 emoji prediction, language modeling. So if you're texting and you see that your phone suggests a word or a spelling mistake that you've done, that's language modeling, that's language prediction. Speech recognition, this is actually from audio to language, to text language. Caption generation, also capturing an image and then from there describing, say, the contents of that scene. Machine translation. There's a couple of things you can do. Document summarization, question answering. So like, how does Siri understand what I'm saying? Natural language processing. All right. So as you'll see, this problem isn't as trivial to solve. We see text, we see tweets, and we recognize exactly what's happening. If it's a happy tweet, if it's a sad tweet, but it's a little bit harder for computers because all they see is ones and zeros. So emoji prediction is, again, text classification. So, I mean, if you look at this picture, right, you give it an article and it can determine which genre. So if you switch that to emojis, you give it a tweet and it'll return, say, which emoji it might suggest for you. As you can see, you can also do sentiment analysis. And sentiment analysis is also kind of like text classification. You just replace the genres with the different sentiments. You got happy, you have sad, you have neutral. So yeah, this is machine learning, natural language processing, language all interacting as one. All right. So now let's move on to emoji prediction. So you're gonna hear me talk about documents and labels and targets. And what I mean when I say documents, I'm gonna be talking about tweets. I'll try to change, I'll try to correct myself if I do say documents. But basically, we're gonna be creating a model that given a tweet will be able to predict which emoji should be used. So there are kind of stages to machine learning in general, not just natural language processing. We're not really going to show the data mining, that's just getting the data set, but we are going to be focusing on pre-processing, which includes feature extraction. Also, I should mention that this is a pretty basic application. It's not going to go super into depth, but we have pre-processing, feature extraction. Feature extraction, we'll cover what features are and why they're important to machine learning, and training. And the type of training we're going to be doing is supervised learning. So there's a couple of different types of learning when it comes to machine learning. There's unsupervised learning, there's supervised learning, the one we're going to be doing, and there's other types. So I'll kind of differentiate what supervised and unsupervised is. In unsupervised, say you give your model, you give your algorithm, your training algorithm, you give it a data set. Say the data set is pictures of cats, or cats and dogs, a picture of data set of cats and dogs. There are algorithms that are used to separate these. And so this algorithm, unsupervised, would just cluster them. It won't know what it is. You're just giving it the pictures. So supervised learning is you give this model, you give it your data, but you also give it your label. So you say, this is a picture of a cat. And that's what it does. The algorithm will recognize that. And so next time you give it a picture of a cat, it'll be able to recognize it and say, this is a cat. So the way we're doing it, we're going to give it a set of tweets and its corresponding emojis. Cool, so let's look at our data. So the project that I chose provided a script that did the data mining for me. So I did this, I don't know, 2016. So this reflects whatever was happening in Twitter in 2016. I don't know, I don't want to know. These are the tweets, and these are the emojis, but they're just numbers. Yes, but these are the mapping tables. So let's try to see if this makes sense. So for this tweet, the emoji that corresponds to it is this 2. So what is this 2? This is this emoji, face with tears of joy. What an explanation. Okay. So let's look at the second one just to show you that it actually is what it is. So here you see the word Christmas. They give it this emoji. That emoji was included in this tweet. And here it is, a Christmas tree. So how these were gathered, the script makes sure that it's only tweets with one emoji just to make things easier. And then it separates them into its words and to the emojis in the tweet. So this emoji was included in that tweet, and so on and so forth. Okay, so this is where we actually see some of the code. So how do we do this? So the library that my friend used and told me to use was sklearn, the SciKit library. And it was pretty easy, pretty straightforward, so that's what I used. These are going to be used, are the modules we will use for feature extraction and sort of the pre-processing. And again, we're not getting too intense with pre-processing. There's a lot of things you can do, and you'll see later. But we're just trying to make a basic app. These are the classifiers. The one we're going to be using is going to be the neural network. Again, there are these classifiers, these different algorithms. Some are better for text classification, different types of machine learning applications. I just use neural networks because they're good and it sounds cool. But again, maybe it's not the best one. It's pretty good. However, I did this on a 40,000 tweet data set, and I think I had to run it overnight, and it still didn't finish. So we're just going to use a 1,000K data set for this example. Okay. So first, this is the kind of pre-processing step. We're going to organize our data. So all we have to do is read. We're going to read this document, the 1,000 tweets. And we're going to read the 1,000 labels. These are the emojis, and we're going to put them in lists. And I'm going to print them out right here. And as you can see, it reads line by line, and each index, each entry in this list is a tweet. Same with the emojis. We're going to go all the way to the bottom. It's going to read this document. It's going to read line by line, and it's going to separate it. So index 1 of this list corresponds to index 1 of this list. Index 2 corresponds to index 2, so on and so forth, until we get to index 999. Cool. All right. So this, although you can't tell, it's literally just 4 lines of code, is where the heavy lifting is happening. So here we have something called a count vectorizer, and we're going to call this function right here. So what is this function doing? What is this count vectorizer? So this is where we're learning the vocabulary dictionary, and we return a term document matrix. And a count vectorizer converts a collection of text documents to a matrix of token counts. What in the world does that mean? Okay, so there's a couple of concepts. There's a couple of ways you could approach this, and these are kind of this is the way we're doing it. We're gonna get these tweets. And each tweet, we're gonna use this model called the bag of words model. And so let's open this up real quick. Let's see if it has any, yeah. So the bag of word model, in terms of text classification, is basically, we're gonna get a sentence, we're gonna get a tweet, we're gonna get a document, and the features, the things we're gonna use to differentiate different categories are gonna be words. So this sentence right here, John likes to watch movies, Mary likes movies too. It's gonna be made into a type of, kind of like a count frequency type of situation. You have your words and the number of times they appear. So these words will be weighted differently, and we'll discuss how the feature extraction part of it happens later. But yeah, this is what we call, as far as text classification, a bag of words model. It's pretty simple. Okay, I have an example here of different types of why this might not be the best. So here you have 2 different sentences. Let's go ahead and go through it. John likes dog yells. This sentence doesn't make sense, but we're just gonna use it. In this sentence, John, for some reason, likes the way dogs yell. However, the second sentence, John yells like a dog. We can agree that these are 2 completely different sentences. However, with the bag of words model, if you do a little pre-processing, remove stop words like a, do some lemmatization, which is shorten the words, you get 2 identical bags of words. But we already agreed that these are, obviously, they mean different things. So that's why text classification isn't necessarily a super trivial thing, right? These are 2 different, we can recognize that. One way to fix that, we're not gonna do this in our example, but one way to fix that is this n-gram model. So you can choose how many words into one token, one feature would appear, and it just gives the sentence a little bit more context. And the reason I wanted to show is just to show that, you know, this isn't a super trivial, this isn't a super easy task, you know, just predicting, just seeing a document and seeing words and for a computer to know, okay, yeah, this is what that means. So the way we're gonna represent this to our algorithm it was going to use this thing called a document term matrix, term document matrix. So all this is for each tweet, each document, you have this bag of words, and it's represented in this sort of matrices. And as you'll see later in this classifier, or when we actually train the data, actually we'll get to that later, this is kind of the easiest way to hand off the data we captured. So cool. Let's move on to features. As we already said, the words, as far as text classification, these are our properties, these are our characteristics that we're going to measure and use to differentiate between categories. So in our case, the words, the text are what we're going to use to differentiate tweets and which tweets correspond to which emojis. And so an example for y'all to see how it actually is a hard thing to do. When you think of audio, I mean, you can hear me right now, and if I am speaking correctly, you can understand what I'm saying. However, if you go ahead and give this to a computer, like it's literally just waves of sound, different amplitudes, different frequencies, different wavelengths, and it has to use this to be able to predict a word. You know what I'm saying? So when you're talking to Siri, how does Siri know? It literally just sees amplitude, frequency, and time. Images, how does a computer, you know those apps that you can take a picture and it tells you what you're looking at? How does that happen? All it's seeing is pixel values. So it's kind of the same with words and language and computers processing text. All it's seeing, okay, right now we're seeing words, but that's not what the computer is seeing, and I'll show you later. It's seeing numbers. And so how does that work? How do you get from numbers to actual understanding of a sentence and then an accurate prediction? So the next part of this right here is what we're going to use to normalize this term document matrix. So how do we normalize? What does that mean? Okay, I'll show you. So this is a complicated algorithm. I'm going to open this real quick, see if it even makes sense. It does not make sense. So I'll just talk about it. So this makes more sense actually. It's just a measure of originality. So what this is saying, and I'll show you here where you can see better. It's basically a way, as far as feature extraction, to say which word has more weight when it comes to differentiating between documents. So let's see this sentence or this dictionary of this document, the summation of these two documents. So we have the words, the car, truck is driven on the road, highway. Okay, so here is the term frequency count for document A, term frequency count for document B. So both of these documents have the. One of these documents has car, and as you can see, it kind of alternates. So we can agree that if we just take term frequency, that's probably not a good feature, because words like the, words like is, words like a, they're completely going to overload the term document frequency count. And if we rely on those, and then we just rely on term frequency as a feature to say, yes, this word appears a million times, so therefore it appears a million times for this type of document. So whenever we see that, we really don't want to take that into account. So a way around this is this complicated little, this is one of the ways, to normalize data. And so we take this, and you can see it gives it a weight of 0. It gives the word the a weight of 0. Why? Because it appears everywhere, so it must not help. And then it gives car and truck kind of equal weight, and also road and highway. So as you can see, it chooses which features probably have more weight. And so when it comes to text classification and figuring out what should go to where, we really want only to take into consideration I mean, any type of machine learning classification problem, you only want to take into consideration, you know, words that would make sense, original words, words that actually get you something. So I'm gonna go, so right now, this doesn't really show anything because this array is way too big. So I'm gonna just change this, the tweets we're getting, and I'm gonna use these two documents, test tweets and test labels, which is the same, but it only has 10 of them. So it'll show you how this works. So let's run everything again. And let's show you what happens. Okay, so now we have a lot less, but now we can see what's in the term document matrix. And when I say, what is the computer seeing? We see that these are the words. We see that. But right now, when we give it to the classifier, we're only giving it this. And so what this is, it's just, so this word is this index, but the computer doesn't know that. This last word is this index, but the computer doesn't know that. And so these are the tweets. These are 10 tweets. And in this term document matrix, it only has this word, this word, this word, this word. That's 4 words. So let's just show you the tweet. Yes, 4 words. I don't think it's counting this. Cool, cool, cool. All right. So the next thing we call is this, and we print this out, this normalized term document matrix. Let's see if it did its job. It looks like it did. It takes the tweets and it assigns, you know, it weights the words depending on how many times they appeared. The words that appeared less are probably going to get a higher weight because they're more original. So cool. Now let's just bring it back because this model won't converge with a data set that's small. And let's run it again. We're almost at the end. It's mostly understanding concepts because, again, the code is like literally 10 lines. Cool. All right. So what have we done thus far? We got the tweets. We got the emojis. We used this function count vectorizer to get a term document matrix. So bag of words expressed as a list of tweets and their counts. And then we use this function TF-IDF transformer and we do this fit transform. We give it the term document matrix and it returns the same term document matrix but normalized, now with normalized weights. So what do we do here at the end? This is where we make our machine, quote unquote, learn things. So let's explain pretty quick what's happening here. So this is where the supervised part of the learning comes in. You're not only giving it the normalized matrix, term document matrix, but you're also giving it its corresponding labels. If this were an unsupervised learning algorithm, it would only need this right here. And it would, through its algorithm, through its clustering algorithm, or however it chooses to do, it would separate, it would make categories based on how similar each feature is in each category. So we are abstracted from exactly what's happening. Again, this is a neural network, and all you have to do to choose which classifier you want is literally you just import the library. What am I importing? From sklearn, I'm importing the MLP classifier, which is just a neural network type of algorithm. We do not see the algorithm because turns out machine learning is very statistics heavy. That gets nasty. And right now we're just covering how do we use it, not how does it work. So let's get back to what's happening. This is supervised learning. And so what it is creating is a classifier. So to simplify what a classifier is, think of a function. Let's think of algebra. Let's think of f of x. So what this is giving us, what it is returning, is that function f of whatever. So if you think of it in terms of the function, You're using an algorithm, an MLP classifier, to create this function that, given a tweet, will return an emoji. So let's test it out. We have here, classifier has a function that you can call, a member function called predict. So literally all you have to do is you have to give it some tweets and it will return its predictions. So we have our classifier that we trained using supervised learning. And now we're going to predict and test how good this classifier was. So this is, you're looking at it, this is machine learning. This is it. You give it the data, these are tweets, you give it the emojis, supervised learning at least, and you have yourself a classifier. That's one line. So this is what I mean when I say the heavy lifting happens here, where you read the data, where we didn't do a good job because this is a simple app of choosing, being very careful about which features are better. We just do something super basic. But this is where the heavy lifting really happens. Oh no, did I move it? Yes, I did. Okay, we're back. So the heavy lifting happens here, and the easy part is here. We just give it, we say, okay, this is what we got. Do your thing, algorithm. So let's see what happened. So we give it a list of tweets. These are the tweets, but they're, represented as literally zeros and whatever numbers. It doesn't see any words. It just sees indices and weights. And we expect it to come back with, maybe good answers. I mean, again, this data set is literally 1,000 tweets. That's not very good as far as a good data set, because that's not a lot. But we give the predictions, we give it the tweets, we say predict our stuff. So F of whatever, we give it the tweets, this function, and it returns the predictions. So what do these predictions look like? It looks pretty similar to what we have. So another cool thing, this library does everything for you again, which I love. There's this function that you import. Let's go all the way back. sklearn.metrics, import accuracy score. You give it the predictions, you give it what the actual answer is supposed to be, the emojis. If you remember at the beginning, it's just the order of the emojis. It's just the line by line. It's in a list, sort of like this. And as you can see, the accuracy score for this is 0.998. I'm assuming 1 is a perfect score. So is this a great classifier? I would say no, but what we're seeing is, it's showing almost 100, which again is supposed to be a perfect score. But this model, all it's saying is this score, all it's saying is that this classifier, that this function is good at predicting things it already saw. So that is basically it. I hope I covered it well. I don't know. Do y'all have any questions? I think that's all I have for y'all. But again, I'm here to I'm happy to stay and explain things, because as I was going through this tutorial, I was remembering things that I didn't even remember from this class. So I might have skipped things, and this run through was very different than my last two. So do y'all have any questions? Let's see. Yeah, I'm just going to open it up for whatever comments and questions y'all want to make. Can I share the Python notebook as like it on GitHub? I believe it's on the GitHub.
Looks like someone has a question.
Where's this question?
Rosemary?
Yeah, that's me.
Oh, awesome.
Hi.
Hello.
Hello.
So I know you mentioned that the SciKit library was pretty straightforward.
Yeah.
But was that because you're already familiar with the concept, or?
Yeah, that's one thing that I was going through this and I was thinking, okay, I only know this because I took this course. And so I mean, if you look at this, right, it looks straightforward, right? The actual line where you actually make the model is just this, but how do I get there? How do I know to get this? That did take some reading, right?
Yeah.
That's where the whole feature extraction stuff comes up. And I mean, there are a bunch of tutorials online, but what you do have to know is that this feature extraction problem, it's not super trivial. It's not super easy. As you can see, like the computer doesn't see words, it sees, you know, ones and zeros. And in these different applications, like audio and image processing, you know, how do we choose the best features? And a lot of these algorithms help you with that, but in the end, it's you who has to be tuning this and kind of figure out, okay, what is a good feature for predicting, say, documents? Is this a fake news document type of thing? Does that make sense?
Yeah, I think that makes sense. You sort of have to figure out.
Yeah. It's not an easy problem. It takes. Yeah, this course made me cry. So if that answers anything.
Well, thanks for that assurance. But yeah, I think that does help.
But again, it's doable. It's totally doable. It's like, it's an art. I read the super cool article. There's a lot of Medium articles, and they break this stuff down pretty easily. And sklearn actually has tutorials of its own for different types of things. Like there was this cancer prediction thing that they went through. It's pretty cool. You should check it out.
All right, will do. Thank you.
No problem.
So I wanted to share something I forgot, and I don't know if you can open that link, Alex, when I send it to the chat. Can you open it really quick?
Am I in the right place?
In the chat for the Zoom.
Oh, okay. Cool.
Are you able to see that in the menu on top, or maybe
here it is.
It says chat. Okay. So if you see that we have all the events that we have done, they are here. So if you scroll a little down, Alex, please.
Yes.
You will see.
My bad. Let's go back.
You will see all the events and all the GitHub, all the information are there. So hers is there, is the second one. So if you click over there in the picture, you will get the all the information.
Wow.
So, and also you can go through the other ones if you want to go back. So this is the one for the Python track. So we have all the webinars we have done in there.
Sweet.
Does anyone else has another question?
Let's hear it.
No one? No one else? Well, we hope this information has been helpful for you tonight, and we want to thank Alex to spend the time to explain us this. And
somebody has a question.
Oh yeah?
It says.
Oh no, it just says type in one moment. Okay, perfect.
Cool.
Let's just give it a minute. Yes, sure.
Also, if anybody has questions outside of this, I would be happy to answer because I realized there was a lot of concepts here.
And if you want to talk and you raise your hand, I could give you the ability to talk. Okay, there's someone right.
At the moment you plug in training data for the predictions, how would you normally split the train test data for natural language processing? Could you elaborate? What do you mean normally split the train test data? Sorry, could you clarify? Like, could I do a better job as far as testing this? 100%. There's something called k-fold validation. Let me look it up real quick. Let's see if there's a good picture for this. I don't know if I'm answering your question, but I'll explain what I think your question is. And And I think you're asking, how do I yeah. Okay. So there's a way you can, obviously you can go and retrieve more tweets, but there's this way you can use your data set and, you know, train only certain parts of your data set, use this as training, and then test your data with things you don't use in that training. And then you do that you separate your data set into like K parts, 1 part, 2 parts, 3 parts, however many parts. And the training is the bigger part. The test data would be the smaller part. At one point, I believe this repository had functionality for that, although I think I implemented wrong. But that's kind of the concept, is you use part of that data set to train and the other part to test. So that's one way that I was taught that you can do, you know, for actual testing. Maybe this is a better graphic. First of all, you train this, you test, and it gives you a measure of performance. So I think I answered your question, hopefully. Let's see. I think I try to do it here. Yes.
Yeah.
Try
Yes.
to do it here, but it wasn't very good, so don't use that. Cool.
So does anyone else has another question before we end? No one? No, I think we're good to go. Seems like.
Awesome.
Well, thank you for everyone for joining tonight. Thank you, Alex, to spend all the time putting this together and sharing it with us.
Yeah, no problem. Happy to.